Hello everyone, so today we're going to look at another proof. So last time I proved that if f was differentiable, it was continuous at a single point. So today we're actually going to prove something a little bit bigger, which is that if f and g are differentiable, then the derivative of the composition is equal to f prime of g of x times g prime of x. So this is known as our chain rule, and it is one of the most important rules for derivatives because it occurs pretty much everywhere. So there's a couple ways we can approach a proof. So kind of a very simple proof would be to say that dy dx is equal to dy du times du dx, where that's going to be y prime of u times u prime of x. And note u is just going to be some function of x, which in this case would be g. So we can kind of sneak in this du expression. Now the problem with that, though, of course, is the fact that du maybe equals 0, right? So we're not sure, depending on the properties of the function, it might equal 0. So what we're going to work through is a much more careful version of the proof. And even this proof is going to be not quite the most rigorous, but it's going to be much more rigorous than just looking at those differentials. All right, so we're going to start by noting that we're going to assume that f and g are differentiable. So we're going to start by looking at g prime. So I'm going to want to look at both g prime and then f of g prime. So g prime of x is equal to the limit h goes to 0 of g of x plus h minus g of x all over h. So our standard definition. But what I'm going to do with this equation is I'm going to rewrite it slightly differently, because we're going to need to build up a little bit of machinery to work through our proof here. So we'll just note, if I took the g prime of x on the left-hand side and subtracted it over, that would be the same as saying that the limit of the difference quotient minus g prime of x is equal to 0. Pretty obvious. Okay, so what we're going to do then is we're going to kind of make that into a function. So we're going to let, and this we're going to call expression 1, we're going to we'll use a different letter, maybe v of h equal the piecewise function g of x plus h minus g of x all over h minus g prime. And that will be where h is not equal to 0. And then we're going to make it 0 at h equals 0. Okay, so we're going to need to use this function later on, hence the numbering there. So let's just take a note that the limit as h goes to 0 of v of h is equal to v of 0, which is just 0. So note v is going to be continuous for all h, right? We would be worried at 0, of course, because our value doesn't exist there for that g of x expression. But we're just 0 at 0, and the hole is filled in, actually. So that difference is going to approach 0. So v is a continuous function. So that's going to be very useful for us. So now what we're going to do is we're going to take that function expression. So note, if h is not 0, v of h is equal to that g of x plus h minus g of x all over h minus g prime of x. So we're going to take that top expression for our piecewise function, and then we're going to manipulate it a little bit more too. So we're going to take the g prime of x, and we're going to add it over. So we're going to end up with plus g prime of x equals g of x plus h minus g of x all over h. And then I'm going to multiply both sides by h, again assuming h is not 0. So we have a non-zero expression, so we'll have h times v of h plus g prime of x is equal to the difference of g of x plus h and g of x. And then finally, I'm going to solve this for, or isolate this for g of x plus h. So note g of x plus h is going to equal, if I add the g of x over, and then I'm going to have this undistributed product that we had on the left side. Okay. And again, we're kind of building up this machinery, but it's going to have a purpose for it. So we're not just doing it for the sake of doing it. We're going to call this equation 2. So this is going to be important for us. So really what we've done is we've manipulated g prime. We've manipulated g prime using its limit definition and then renaming this function. Now we're going to do the exact same thing, and we're going to do it for f of g of x. So we can say similarly for f. So what I'm going to do in this case, though, is I'm actually going to let, because we have this g of x and x, I don't want to confuse variables, so I'm going to use the letter z instead of x for now. So note z is just another variable just like x, but I'm going to avoid confusion of that x floating around by just using a different letter z. So I could do the same thing for f of z, so f prime of z is going to be the limit as h goes to 0 of f prime, f of z plus h minus f of z all over h. And then I could run through the exact same argument that I did for g prime. So what we're going to do is, instead of a function v, we're going to name a new function w. So we're going to say, and let me be slightly more careful. Let's go back. We're going to drop h, because we actually don't know that h is going, that the value we're approaching is going to be similar. So I'm actually going to use a different value than h as well. I'm going to use the letter k. So just because we don't want to assume h is the same for both values. It could be different values both approaching 0. So h and k, so we're going to use k, not h, for our expression here. And that'll be useful later. So just note, we're just using some alternate variables, still describing the same definition of the derivative though. So then I'm going to define this function wk exactly how we did it for g. So, but now we're using f, of course. So we'll have f of z plus k minus f of z all over k. So that's our derivative minus f prime of z. So again, I'm kind of skipping those steps because it would be the exact same expression that we derived using g, only now instead of g prime, it's f prime. So we've got w of k, and then 0, and then we'll note this is for k not 0 and k equal to 0. Okay. And we can note here as well the limit as k goes to 0, w of k equals w of 0, which is 0. So w is also continuous for all k. Okay. So we've got that, and we'll name that equation number 3. So that's going to be equation 3. So we've got 1, 2, oh, sorry. That's not going to be number 3. And then what we're going to do is do the exact same thing. So we'll also rewrite v like we did v. We'll rewrite when k is not 0. So note k is not 0, then w of k is equal to f of z. Let's try that again. Z plus k minus f of z all over k minus f prime of z. And then we can resolve this in the same exact way for f of z plus k. And what we're going to end up with is f of z plus k times w of k plus f prime of z. Okay, and that's going to be equation 3, that f of z plus k expression. I think I need to add a parenthesis here. All right, so note we've got a new expression for f of z plus k. We've got a new expression for g of x plus h. And then we've got these v and w functions. Okay. All right, so now we've got all the machinery that we're going to need for our proof here. So let's get to it. So let's consider the derivative with respect to x of f of g of x. So that is going to equal the limit as h goes to 0 of f of g of x plus h minus f of g of x all over h. So now we're going to use those formulas that we had above there. So if you look back up in your work to g of x plus h, we'll end up with the limit as h goes to 0 f of, and so g of x plus h was the same as, maybe I'll use a different color here. So g of x plus h times v of h, oops, not v prime, plus g prime of x. So that's using equation 2. So that's by equation 2. Whoops, let's do red. So again, from above here, equation 2. So we're just putting that back in there. And then we'll keep everything else the same. So minus f of g of x all over h. And now we're going to make a convenient substitution. So we're going to let g of x equal z. So g of x is just going to be some value z, some variable quantity z. And then we're going to let k equal h times v of h plus g prime of x. So we're going to make this convenient substitution that's going to allow us to get something really, really nice. So now we're going to rewrite that limit with those two substitutions. So we'll get equals the limit as h goes to 0. So now it's going to be f of z plus k. So note, oops, that is z. That whole thing is now k. And then, of course, z is going to be used again over here. So we're just substituting those for some new letters, but those letters are going to be familiar because they're what we used to define f earlier on. So we've got f of z plus k minus f of z all over h. But now if we think of equation number 3, we had this expression for f of z plus k. So f of z plus k was the same as f of z plus k times w of k plus f prime of z. And then that's going to be minus f of z all over h. So we went from here to here by equation 3. So we're using equation 3 here, and we'll see that this is extremely nice because now our f of z's cancel. And what we end up with is the limit as h goes to 0. Now we're going to have k, w of k plus f prime of z all over h. But if we recall, k was equal to this guy. So we're going to resubstitute that h, v of h plus g prime back in. This is equal to the limits as h goes to 0 of h, v of h plus g prime of x. I think that was all of it, right? V of h plus g prime of x, yes. And then times the remaining quantity w of k plus f prime of z. Okay, good. So we'll note we're just replacing k with what we defined it as. So all of that is really just k. But again, we'll see that this is going to result in some very nice cancellation. And I think also I'm going to rewrite, well, let's go ahead and wait a moment. And so let's rewrite what's left in our limit here. So that's equal to the limit as h goes to 0 of v of h plus g prime times w of k plus f prime. And then we'll notice some things here. So first, this is really just f prime of g of x, because z is g of x. And then we'll note that the limit as h goes to 0 of v of h is equal to the limit as h goes to 0 of w of k, which equals 0. So that was from our earlier definition of v of h, and then v of k, if you remember, k has this h times a quantity in it, so it's just going to be 0 times that quantity as h goes to 0. So both of those are 0, which means this is going to be 0, and this is going to be 0. So then what we end up with is that this is going to equal, now note, g prime of x has no h in it. So the limit doesn't depend on h, so g prime of x is like a constant. And then f prime of g of x also doesn't have an h associated with it, so it's independent of the limit. So these are going to be unchanged, so it's really going to just end up as the product of those two remaining expressions. So we'll get g prime of x times f prime of g of x, which is a slightly reversed version of that. But regardless, it is proved. So g prime of x times f prime of g of x is the same. Where did we put it? As the derivative with respect to x of f of g of x. So you'll note there's quite a few steps in this process, kind of a longish proof, but a little bit more careful and a little bit more worked through. So I would highly, highly recommend, looking over this maybe once or twice just to see if you can follow along with it. And hopefully this provides some help for figuring out why this is true and why this chain rule applies. And you can imagine if we went to higher dimensions and we had more variables, the proof of this is going to change and become a little bit trickier. But that is the end of the proof. So if you got questions, email me or come by the office hours. Otherwise, until next time.